I was the first person in my family to go to college, so I just went very close to home at a university called Clarion University. It's just a state school in Pennsylvania. Not many people know of it, but it was very cheap, and I was paying for a school myself. So that was the decision I made at the time. And it turned out okay, because I got to go to places. And so, I'm from Pennsylvania, and Clarion's near Pittsburgh. But I got to go places to do research over the summers. This black arrow is supposed to be pointing down to Tennessee, where I was in Oak Ridge National Lab for a summer. And then I also spent a summer in the UK. And these programs, they're called REUs, Research Experiences for Undergraduates. If you don't know about them yet, it's okay, because freshman year, you're still getting into the swing of things. You're probably not sure which direction you're headed. But they're very good programs. Keep an eye out for them. If this goes for research experiences, but also any questions you have from my talk, please feel free to reach out to me via email. And if you don't have it, please ask Tyler for it, and he can pass it along. But yeah, if you have any questions about sort of my path through physics, please feel free to reach out. I spent a summer in the UK, came back to Clarion. And when my senior year, I applied for a program that would fund me to go to the UK for a year to do a one-year master's. And I ended up getting that, which was great. Got to spend some time there and live in a different country for a year, which was really enjoyable. So I deferred for a year and then came out to Boulder, which is that last arrow over to Colorado. And here I am now. And I just want to highlight or share a few photos, because certainly when I was a freshman, I did not know where physics could take you. And I think one of the coolest things about being a grad student and just going through physics, not necessarily just physics, but like physics, math, and computer science graduate schools are almost always funded fully. So you don't have to go into extra debt to get that next degree after undergrad. And that's really nice. But in addition to it being funded, so your tuition and a stipend being paid to you for doing research, aside from that, you also get to go to really cool places. So University of Birmingham is where I got my one-year master's in the UK. I got to go to Dublin, got to go to Rome for a conference. There's a school in physics, a school in France called Les Houches. They host workshops in summer schools where people just come from all over and present their research, and there's lecturers that come and talk about specific topics. And I just, I had no idea that was out there when I was getting started, but just wanted to let you guys know that there's a lot of really cool things that that physics can lead to. And I mentioned the height of Mont Blanc only because people in Colorado never shut up about 14ers. So just, if you get to go there, you can climb something taller. And then this was all supposed to be in person. So I was hoping that there would be a more natural way to ask questions, but I was going to give a piece of trivia of wondering if anyone knows whose door this is in Edinburgh, Scotland. Very famous physicist. I guess the trivia doesn't work quite as well over Zoom, but if anyone knows, if they can unmute and say their guess for whose childhood home this might be, and if not,
James Clerk Maxwell, perhaps.
Yes, I didn't know how long to wait before the awkwardness, the silence. Was too much, but yes, exactly. It is Maxwell. So whoever said that, I cannot see, but very good. Okay, so that was just to share, a bit about how I got into physics. And at the end, I'll talk a little bit about what it's like being doing theoretical research versus experimental. But now I want to get into sort of the meat of the talk and talking about entanglement. And it's gonna, like I said, there's gonna be a good bit of jargon. And so the things that I think are gonna be most confusing, I'm gonna iteratively come back to. And we're going to keep picking away at it until at the end, we hopefully have a nice mathematical description of what entanglement is and why it's useful, but why it can also be detrimental to things that we try to do. So I'll explain all these in turn, but we're going to start with something called the EPR paradox, which maybe you all have heard of, but the EPR stands for Einstein, Podolsky, and Rosen. So this is work that was done in Princeton, the Institute for Advanced Study, where Einstein was for the later years of his life. And collaborators at the Institute for Advanced Study. And so the idea here is this particle on the left, like in classical mechanics, we write down, these pictures before and after when we're conserving things. For instance, if particles collide, we might conserve linear momentum before and after. We might conserve energy before and after. And so these pictures are a nice way of like reminding ourselves what's happening. But this is a little bit of particle physics, and we're not going to go into the details, but I don't want you to get bogged down in them. So I'm just going to say the particle on the left has something called spin. The particles on the right have something called spin. And you might not have heard about spin, but it's essentially a quantum mechanical type of angular momentum. It's very weird, and it's one of the most quantum mechanical things that there are. And I don't want to get bogged down in the details, but I just want to say, think of spin as angular momentum for this talk. And even though that's not, maybe not that satisfying of a statement, because you could still ask, well, okay, what is it actually? All I want you to take away so far from this slide is that angular momentum is going to be conserved. And so whatever this particle, which is the pi with a little 0 on the subscript, it's a neutral pion. The 0 means neutral, no charge. And a pion is just the name of the particle. And then on the left, it decays into an electron, which is the particle on the left, E minus, and a positron, which is exactly like an electron, but with positive charge. And so these particles both have spin, but because the thing on the left had no spin, then the net angular momentum, the net spin on the right, has to be 0. So that means if you were to somehow do a measurement and measure the spin of the electron and find it spin up, then you would find with 100% probability, if you were to measure the positron, you would find it spin, I forget what I said now, up and down or down and up. So you will find them in opposite. But before you do the measurement, the weird thing about quantum mechanics is you don't know what state either of them are in. So the way I like to conceptualize this problem is think of spinning 2 coins, and these 2 coins that are completely independent are going to represent the spins of the electron and the positron. And imagine you could keep them spinning. There's no friction, and they just keep spinning for as long as you want. And you go off, to 5 light years away. So there's no way to communicate effectively over that distance. What's interesting and what troubled Einstein, and really why he hated it, was if you were to slap your hand down on one of these coins, which is sort of the analogy for measuring one of them, you would find it in either heads or tails. There are 2 possible outcomes. You're going to find it in one of them. And what he didn't like is this system seems to, even though they're in indefinite like superpositions before, when you do this measurement, you immediately know if you find spin up or heads up, if it's a coin, you immediately know that the other one has the opposite, is going to, if measured, have the opposite spin. And that troubled him a lot. And, we're going to see that the weird thing here is really the fact that quantum superposition is a thing, but this is what he called a paradox when they published it. And this is what their biggest issues were with quantum theory at the time. And so what I want to build up in this talk is an analogy from Leonard Susskind, who publishes a great series called The Theoretical Minimum down here at the bottom. Highly recommend getting a copy off Amazon. It's only like $15. They also have lectures on his site. So definitely, get these slides afterwards or write it down, and highly recommend this. This is the book that I started reading when I was trying to learn quantum mechanics for the first time. And I really think, even though it's not going to get you prepared for, say, the GRE, the test you have to take for grad school or something like that, it really does do a good job of conceptualizing a lot of quantum theory. So I highly recommend it. And the analogy he gives is entanglement is a lot like a mechanic knowing everything about a car as a whole, but nothing about its parts. So if you try to probe the inside of the car, you know absolutely nothing. Classically, that would make no sense. Initially, I was going to use this analogy of me knowing nothing about a car, but that's actually true because I know nothing about cars, so the analogy doesn't work quite as well. But imagine a mechanic trained his whole life to know everything about a car, but as soon as they open up the hood, they suddenly know nothing. And so this might seem completely nonsensical, as it did to me the first time I read it, but as we go through the talk, I'm hoping to build that up in a meaningful and in a mathematical way. A reasonable question you might have is, okay, is this just a philosophical issue that Einstein had? And, was he just old at the time and not really capable of wrapping his head around a new paradigm? And that's a reasonable question. But philosophical things aside, which they are very interesting to think about, what entanglement means for the nature of information and the nature of reality. But those aside, there are other reasons to care about entanglement. And here I've pictorially shown just a few examples of where entanglement is actually useful. And so each time here I say, quantum sensing, quantum blank, quantum, quantum followed by anything. In today's day and age, you should be a little bit skeptical when people say, oh, it's quantum, so it's better. But really the earnest goal of these fields is to use properties like superposition and entanglement to do things that classical methods just can't do. And so one example is quantum sensing using entangled photons or some sort of quantum state of light to do what I've tried to show here as a diagram of like an interferometer, where you might split light on a beam splitter. It might acquire some phase or interact with some sample and then recombine it on a beam splitter and then detect that light. And it turns out that using quantum entangled photons, you can actually surpass the limits of classical methods. And the same is true. The hope is that, we'll be able to surpass classical methods using quantum computers. Maybe you've heard of like IBM, Google, Microsoft, Intel, and then a bunch of startups trying to make quantum computers that genuinely outperform classical computers. Google has claimed that they've done something that classical computers can't, but I'll refrain from comments on that. But the goal of all of these fields is to use entanglement and superposition to do useful things. And so if we were in person, which I'm sad, and Tyler, jump in, like if we're still going to try and do this, but basically at this stage, we were hoping to discuss with your neighbor and say, have you heard of any of these applications? And have you heard of any other applications? And if anyone wants to share, if they've heard of any of them, or if they've heard of any other applications of entanglement or quantum mechanics in general. And Tyler, I don't know if you can moderate that or what.
Yeah, why don't we just, instead of going into breakout rooms or any of that, if you have any responses, just put it in the chat, any key buzzwords or anything, or you can also unmute.
And if not, that's okay. I know it's a lot tougher over Zoom. But yeah, the point I kind of want to make, well, one example of quantum sensing where quantum effects have been used to enhance something called LIGO, which stands for Laser Interferometer for Gravitational Waves. Laser Interferometric Gravitational Wave Observatory is what the acronym stands for. And it's this big, massive 4-kilometer laser, and there's two of them, and they point at right angles, and they basically race off and bounce off a mirror and then come back, and you see if they've if they're perfectly in phase, or sorry, if they're perfectly out of phase, which is how you set the detector up, they're gonna you're not going to get any light out of the second beam splitter. And they use these to detect gravitational waves, because gravitational waves come in and they basically change. They literally stretch and squeeze the arms of these lasers, and they you can detect gravitational waves from, say, colliding black holes this way. And LIGO has actually implemented something called squeezed light, which is a purely quantum mechanical phenomenon. And they've shown that they can actually enhance their detectors in this way. And then, like I said, quantum computers, all these, if you just Google, if you Google quantum computer, you will see a bunch about this. So maybe, maybe we'll just jump into the content, and I'm hoping you'll bear with me, because if you haven't had a linear algebra class, I think this is going to seem like a lot, but I think a lot of you have probably seen the main components of linear algebra. And it turns out that, there's another thing I wanted to share, just because I didn't know it or didn't appreciate it when I was a freshman in college, is that linear algebra really is, I would argue, one of the most important maths you can learn after calculus and differential equations. If you focus only on one other math, I would definitely encourage you to focus on linear algebra. And a great series, maybe some of you know him on YouTube, Grant Sanderson. His YouTube channel is called 3 Blue 1 Brown. And he has this fantastic series called The Essence of Linear Algebra. And I really think for laying an intuition, I don't know if anyone could do, I don't know if it's possible to do a better job than what he's done in this, I think maybe 13 or 14 series. The 14 video series. I really think linear algebra, the intuition should be learned visually first. And so I'm going to try and do a lot of things visually, but Grant on YouTube really does a remarkable job. So anyway, I think hopefully a lot of you have heard of vectors. This is just something with magnitude and direction. And so I have a little example here where r hat, this little hat thing, this arrow indicates it's a vector. So we usually represent them using these columns. And, you can, with a coordinate axis, then like the Cartesian plane, just the XY plane, you can specify, okay, walk 2 steps in the X and then up 3 steps. And that describes, where you are in this space. And so vectors are a very compact way of describing, one example is of describing orientation in space. Of course, velocity is a vector, acceleration is a vector, all of these, all these physics concepts that you've probably seen in high school. You see that vectors are a really compact way of describing them all. But things would be very boring if vectors were just vectors and they just stayed there forever. So we want some object that can sort of encode how vectors change from one vector to another vector. And so this bottom picture here, I have this square matrix. And what it does is it rotates the initial vector, x, y, to some new vector, x prime, y prime. And you see pictorially what it does is it rotates it by an angle theta. And so in general, the reason they're so useful is if I just had some arrow pointing in space and there's not much I can say meaningfully about it. It's just some, it's some arrow. I don't know what it is, but I'm going to call this process of setting down coordinates. I'm going to call it choosing a basis. It's like choosing how we're going to represent. I could rotate these axes and describe the vector. The vector would have a different description with respect to some different axes. But once I pick a basis, I can then basically decompose any vector you give me into the basis vectors of that of those coordinate axes. And so if you give me a vector like this, I can decompose it into some step along the x plus some step along the y. And the reason I review this is because this is exactly what we're going to need to describe qubits, which qubits are quantum bits. And so the first question you got to ask is, what is a bit? Well, a classical bit is what your regular old computer operates using. Fundamentally, like ones and zeros. When you see, a hacker on TV or whatever, they always show a bunch of ones and zeros, even though literally no one codes in ones and zeros. That is fundamentally what your phone and what your computer operate. What they understand is some on and off switch. Like a light switch being on versus off can be a bit. And the weird thing, quantum mechanically, and maybe you've heard of Schrodinger's cat, that's like the classic example, is it's alive and dead before you measure. Then you open the box and it's, it's either alive or dead. And that is the weird thing about, there's a lot of weird things to think about with quantum superposition, but here I just want to try and draw the analogy between, okay, we're decomposing vectors into components. The same thing can happen. We're now going to call vectors kets. This is due to Paul Dirac. You can call it vectors, you can call it states, you can call it kets. Doesn't matter. This little object with the line here and the little sort of bracket right angle thing here is called a ket. But really, just think of it as a quantum state. And for our purposes, we're going to be thinking about them as qubits. And so a bit has 2 possible states. So you might think, okay, a quantum bit is also going to have 2 possible states. But the weird thing is before measurement, it can be in a superposition of these 2 states. But just like before, we break up the state into 2 possible vectors. Just like before, we can do that. We can just pick a basis, which we're going to denote 1 and 0 and 0 and 1, just to make the math easy. But also because we need this final vector to be length 1. And the reason we enforce that condition is it basically encodes the fact that the probability of something happening is 1. Meaning you might have a half probability to get 0, and you might have a half probability of getting 1, but the sum of all those probabilities have to add up to 1. And that's related to the length of this vector being 1. We're not going to get into the details of how to calculate it, but that's why you force it to be length 1. So before measurement, you can be in some superposition, but after measurement, so, Schrodinger's cat, you open up the box, you're either going to find the cat alive or dead. And so the example I gave at the beginning was like spin, and I'm going to represent spin, even though it's, slightly confusing to give such a clear description to something that is really like some weird probability distribution. Just so we have an idea in our heads, spin up is going to just be an up arrow, spin down is going to be down arrow. Okay. And I'm going to use these vectors to describe them. And we can visualize these vectors on a sphere. And so I'm going to put the 0 vector up at the North Pole and the 1 vector down at the South Pole. And the point of superposition is now, like, a classical bit would only be able to be at the North Pole or the South Pole, but now a quantum bit is going to be able to be anywhere on this surface. And so it lives on the surface if there's absolutely no noise, no thermal fluctuations, nothing interfering with your system. You can measure it and find out what state it's in. And if there's no noise, it'll just stay in that state, and you'll be living on that sphere in either 0 or 1. And before you measure, you can think of it as living anywhere on the surface of that sphere. And the reason I specify that it has to be on the surface when there's no noise is because what we want to build up to is talking about how we model noise and what entanglement has to do with any of this. So the reason we're building all this math up is so we can have a nice mathematical description at the end of entanglement and a test for entanglement, and that'll tie into sort of the research I've been doing in the past year. And I guess I'll skip the discuss with your neighbor. Again, I think people were more inclined to discuss when they're getting free pizza and we're all sitting in the same room. So I apologize again, but and maybe I spoiled it talking about LIGO, but another example of a qubit would be using a single photon, a single particle of light as a qubit. And all you really, the fundamental thing between these is you need to be able to distinguish between two distinct states, right? Like a light on, a light off, you can distinguish between those. But quantum mechanically, you need some measurement that you can do that's going to distinguish between these two states. And then once you have these, reproducible results where you can distinguish between two different states, and then you can collect statistics, then you can start really doing stuff with, quantum information and qubits. And so one example is if you had a polarizer. So polarizers, like you might have polarizing sunglasses, and they're designed to only let certain polarizations through. And there are two perpendicular polarizations. And so maybe you set up your polarizer so it only lets vertical through. So this photon that didn't get through must have been horizontally polarized, but a vertical one will get right through. So now, we can start thinking of using photons as qubits. And there are companies, one off the top of my head is called Xanadu, based out of Canada. And they just got hundreds of millions of dollars in funding to try and build a optical quantum computer. Psi Quantum, PSI Quantum is another company with a ton of funding to do the same thing. So this is a very real thing. But for us, we're just going to think about these particles that have spin. And the more you study quantum mechanics, the more you're going to meet spin, which is why I want to focus on it. It's because it epitomizes a lot about what makes quantum things quantum. So one of the cool things about linear algebra, in my opinion anyway, is if you give me two classical numbers like 3 and 5, there's only one way there's one prescription on how you multiply those two numbers. There's nothing, once you learn these rules in elementary school, that's the only rule you need to learn, right? You learn multiplication tables, and eventually you learn tricks for multiplying larger numbers, but there's only one way to combine them. But the cool thing about linear algebra and the basic objects of linear algebra, which are these vectors, is there's multiple ways to combine them. So maybe you guys have seen like the dot product. That's another name for that is the inner product. That's the one I have here in the top left. It takes two vectors, one that you tip on its side to remind you how to do the multiplication, and the other that is a column vector. It takes those two vectors in, and it gives you out just a single number. And so you see this when you talk about work in mechanics. You see this when you calculate lengths of vectors, and a lot of different cases you want to know what the dot product is. Again, 3 Blue 1 Brown, Grant Sanderson on YouTube has some fantastic visualizations of what the dot product is really doing and what it means. Highly recommend. But so that's maybe the first way we learn about combining vectors. And one you maybe haven't seen, I certainly have not seen it as a freshman, is called the outer product. Takes in two vectors, gives out a matrix. We're going to see in a minute, we're going to circle back to why we want to talk about that at all. And tensor products, perhaps the most useful for entanglement. It's this way of combining, basically doing all the multiplications of the components by all the components of the other vector to give you a bigger vector. So in one case, you get a number, in one case, you get a matrix, and in one case, you get a larger vector. And because I suspect outer products and tensor products have not been seen before, we're going to go through those in some detail. And we'll see why we want to do this down the line. But I just want to do one quick little computation to show you. And it's basically you give me any ket or state vector, unit vector, whatever you want to call it. This psi is usually the symbol that represents a generic quantum state. And you give me any vector and I can generate for you a density matrix. And the way I do that is I just take the vector, And like you saw here pictorially, I'm just gonna, it's called transposing, but just making the column a row. And then the way the multiplication works is I just do the top one times this first one, and that's my first entry there, and I get a 1. And then I do the top one times the rightmost 0, and I get a 0, and so on, filling up the rest. If you haven't seen this before, just Google outer product, or just Google, any of these products, and you'll be able to see and do some examples. And the point is I can represent now any state using just this matrix. And you might say, okay, well, the vector is easier to think about, so why even bother with the matrices? And that's what we're going to see as we progress. The reason fundamentally is with just state vectors, it's really hard, if not impossible, to talk about noise. And noise is an inevitable part of any experiment that you're going to do. And so these density matrices, although you don't see it yet, are a way of encoding information about the noise and seeing how noisy our state is. And it's also very useful for when talking about how entangled a state is. And so that's why I introduce it now. But the fact that the initial vector was length 1 is going to correspond to the sum of these diagonal entries being 1. So that's, again, related to probability summing to 1. And so maybe you haven't seen this before, but it's really just it's an easy algorithm to learn once you've seen it once. And I think the same is true for tensor products, though I do think that tensor products are a little bit more foreign, I guess, even more so than the outer product. There are some great, I actually forgot to link at the bottom of this one, unfortunately. There are some great blog posts about the tensor product. One's called Tensor Product Demystified. If you just Google that, I forgot to link to it, but it's by one of the best that I've seen blogs on sort of advanced mathematics. But here I just want to show you the process. We're gonna see in a specific case what the process is, but this is just a generic vector A, tensor B. And so the quotes there mean that that's how you say it. And that little O times, circle with a cross in it is the tensor product. And the process is you just want to do all the multiplications, all the possible combinations. So you're going to put the second vector, you're going to put it twice so that you remember to do the multiplication on both here. And you're going to get A1 times B1, A1 times B2. And you're just, you're going to do that multiplication out where you multiply the A1 times B1, A1 times B2, and so on. And you get this, you see that we start with two-dimensional vectors and we end with this four-dimensional thing that has, so it's a larger vector out. And the reason we care about this at all is because it would be very boring if we could only describe one quantum spin. If we could only describe the state of one electron, we wouldn't be able to talk about our initial experiment, which is the whole point of this talk, is talking about the EPR paradox. And you might think, okay, I forgot we were talking about that. I understand it's a lot of math to sort of try and get through quickly, but without it, it's tough to get to the final punchline. And so this is just the process. You follow the multiplication out, and what you'll find is that two spins up is going to be, we're going to represent it using this vector here, 1, 0, 0, 0. You do this multiplication out, you'll find that multiplication is just based on this process here. And when you get to larger systems, you end up just plugging it into a computer so you don't make any mistakes. But you see that all four of these are different, and that's what we need, is we need four distinct states, distinct vectors to talk about, mathematically and uniquely describe these states. So that's all we've done there. So that's why the tensor product is important. More generally, it's about composite systems. One qubit can be represented by one noiseless, perfect qubit can be represented by just some state vector. Remember, we call them ket sometimes. And if we have two, now we're going to have a tensor product of those two. And once you get to n qubits, which you very much want to have n, you want n to be large in general, because that's when you can really start doing things that maybe classical computers cannot. You're going to just literally tensor it n times. And so you might not know the process, but it's literally just extrapolating this to a larger dimension. And that's all there is to it. But what you can see is already with 2 qubits, we've now gone to 2 to the 2 or 4 entries here. And so if we want to describe all possible states of 3 qubits, we're now going to need 8 different 8-dimensional vectors. And it scales exponentially like that, where the total number of entries we're going to need is 2 to the n. So already, if you're trying to describe 10, 15, 20 qubits, you're going to have 2 to the 20 numbers that you have to store. It starts getting really, really hard for our classical computers to do that, which is why we hope that quantum computers might be able to outperform. So now we're able to circle back to our original goal of talking about quantum entanglement. We've built up a bunch of math and just a few more points, and we're going drive home the analogy, but we're going to have a more mathematical structure to it. And quantum entanglement is just one reason Einstein loathed quantum theory. Superposition bugged him. He has a bunch of famous quotes about why it was so problematic. But every test that we have subjected quantum mechanics to, they have passed with flying colors, and it really does seem to describe our reality, regardless of if Einstein was comfortable with it. And so we're back to the sphere where I said states live on the surface, but I said those were idealized perfect states with no noise. And you're able to store information on those perfect states because they're going to be able to be highly distinguishable from neighboring states, because you have this whole surface area of possible states that it can live on. Any small change is much more detectable from say where this point 1 is to some neighboring point on that sphere, because that's the largest the surface area can be. And then once you start adding noise, we call them mixed states, and they start to creep in to living on the inside of now we sort of think of it as a ball rather than a sphere, where you can now live at any radius, all the way down till the absolute worst case, the case we really want to avoid. And companies like Google, IBM, they're spending all their money and time really trying to isolate their qubits from the environment so that they don't end up with this state 3, this maximally mixed state. Because if you see, let's say I start at point 1 here, and I start adding more and more noise, maybe the qubit is which was initially cooled to a really low temperature, maybe the fridge breaks and now, it's heating up. Well, eventually it's just going to be, regardless of where you start on the sphere, if it gets fully maximally mixed, completely thermalizes and is equal to the environment effectively, it's just going to creep in from the surface all the way down to the center. And wherever you start on the surface, all of those states are going to end up at the center, and they're going to be completely indistinguishable from each other. And so at that point, we say that we've lost all of our information. We know nothing about those states at the center. Wherever you started, whatever you were trying to encode, whatever state you were trying to encode, the more mixed you are, the less you can say about it, because it starts to live on smaller and smaller surface areas until you're all the way at the center where they're completely indistinguishable from each other. And that is what companies are spending billions of dollars trying to fight against. And so we might want to test, is our state pure? And this is the first example of why writing down the density matrix rather than just the state vector is useful at all. If you're just working with pure states, you really can just stick to these state vectors, these kets. So I could easily just describe spin up using this state vector, but remember the outer product, 1 times 1 is going to give me that entry, 1 times 0. So the top 1 times the rightmost 0 is going to give me 0, and then 0 times 1 is giving me 0, and so on. So rho sub 0 is going to give me the density matrix corresponding to this spin up. So now I can say, okay, you give me spin up, I'm going to give you this density matrix. And I might ask, is that pure? And a simple test for purity is, let's square that matrix. Okay, so if we squared this matrix and then asked, and we're going to do this computation in the next slide, and then we ask, is rho squared equal to rho? And you can see, if you've done matrix multiplication, you'll see that this matrix squared is going to be the same matrix. And so we're going to pass this test, and we're going to conclude that the state is pure. But if there was, say, a 1/2 here and a 1/2 here, or anything other than just a 1 in one place and a 0 in the other place, you would not be pure. So if there's anything along the diagonal that is not just equal to 1 and the other entry is then equal to 0, because you need them to sum to 1, if there's anything other than just this, it's going to be a mixed state. And so this is a very granular test. It's very low resolution. We want to be more quantitative with it. And so we're going to introduce an actual quantity called purity. And so this is, if we call it that, it better correspond to something that we want, something we want to quantify, which is how noisy is our state. And so we need to meet one more mathematical object, but even though, the jargon is new, the concept is very simple, and the trace is just going to be the sum of the diagonal elements. So I've indicated visually the trace by just circling the elements that you're going to sum up. But now we're going to square the matrix. So if it's pure, you're going to get the same state back. And so we do this matrix multiplication. We do the top row times basically the inner product of the top row with this first column. So if you've seen the inner product, one of those products we talked about, it's going to be the top left one times the top left one plus this 0 times a 0. And I hope you guys can see my cursor. And if not, highly recommend 3 Blue 1 Browns and also Khan Academy, just anywhere that you can learn about basic linear algebra. But take my word for it that if you do this multiplication out, you get the same matrix back. So if that's all we wanted to know, we're good. It lives on the surface of the sphere. It's pure. There's no noise. But we want to be quantitative, so we're going to take the trace. So this arrow here means implies, and that's just going to imply that the trace of rho naught squared is going to be 1. And so we conclude that it's pure. If the purity is 1, we say it's as good as it gets. That's what Google, IBM, Microsoft, every other company, that's what they're after. They're trying to make as pure a state as possible. And it turns out that we can get even more quantitative and say that the radius here is going to be equal to this quantity here. And you might not see where this comes from. That's okay. There's a lot of math happening in the background, but you can just check the first example we have, which is, all right, let's say the purity is 1. So we go down to this radius of the vector and we see the trace rho squared. We're going to replace that with 1. So we get 2 times 1. We're going to subtract 1. Square root of 1 is just 1. So now the radius is 1, and we know that we're living on the surface. Your state's pure. Okay. But now I want to try a more interesting example. This is the first time we've seen something that isn't just a pure state. And I didn't give it a good name. If I was trying to give you a riddle, I call it rho mixed because it's going to turn out to be mixed. But what we're going to do is we're going to square it. And so that top row is going to be dotted with the first column. So it's going to be a half times a half plus 0 times 0. You're going to get a fourth. And so on and so forth. Again, Khan Academy, 3 blue, 1 brown. If you haven't seen matrix multiplication before, super easy process, but you got to do it a few times on your own to really get the hang of it. What we're going to find is we don't get the same matrix back. And so before, all we could say is it's mixed, but now we can say how mixed. And we sum up those diagonals and we get 1/2. So now let's plug this into our formula. We do 2 times a half, that's 1. 1 minus 1 is 0. Square root of that, still 0. And we're living at a radius of 0 at the very center. This is the worst possible case. This is like Google shutting off their dilution refrigerator that cools their qubits and letting it completely thermalize with the environment. It's going to be indistinguishable. Whatever state you start in, it's going to completely mix with the environment, and it's going to be the exact same as before. No matter what state you start in, you'll end up in this maximally mixed state. You'll be able to say nothing about it, and you won't be able to do anything. And now you still might be wondering, why in the world did we introduce all this? And it's because I want to really give a mathematical statement about EPR paradox. So we're coming back, and we have this neutral pion, and it decays. And we're thinking of these coins flying off in space, and we don't know what state they're in. But at some point, we're going to do a measurement. We're going to find what you would find if you were able to then compare those measurement statistics is you'd find that you would always find, if you find the one coin heads up, you'd find the other one tails. And classically, this is indescribable, because if they're independent coins, there is no reason for them to be that correlated. But quantum mechanically, we see that this is allowed through this like conservation law, which is why, because there's a conservation law underlying it, it's not really that weird. I think it's more of the superposition that bothered the indeterminate, the non-determinism of the situation really bothered Einstein. But the state that we're going to write down, now we can be a little more quantitative. We're going to write down psi, which is this ket psi. So remember, I said that's a generic state. This turns out to be a special state. They are called EPR states or Bell states, but that's unimportant. The point is particle 1. So we'll call this left one 1. We'll call the right one 2. So this is the electron, this is the positron, and the subscripts 1 and 2 just remind you what we're referring to, either the electron or the positron. Well, it's either going to be up and down or down and up. We don't know which, but when we do a measurement, we're going to find out. And so now, even though I know this looks like a busy slide, bear with me and start with the top line. Psi 1, 2 is a state on describing both of these particles simultaneously. It's not just 1 qubit anymore, it's a 2-qubit state. But remember, on the right-hand side here, I have those vectors. So it's really not that scary. I can just take the up-down vector, which is this bottom left one on the right side of the screen, bottom left, and I plug that vector in. And that's representing that first state. And then I subtract from that the down up. So I just take this top right one on the right-hand side, and I plug it in there. And the way you subtract two vectors is just element by element. So I do 0 minus 0, 1 minus 0, 0 minus 1, and I get this final product here. And then remember the outer product, we can always take that state and we can just generate this matrix. Okay. And if we do that, we get this out. We're not going to do the whole computation. You can check it for yourself if you go through the process. I just plug it into a computer because I don't want to make sign errors. And I think in practice, most people just plug it into a computer. But if we square it, So we're going to check for purity. That's what you typically do when you meet an unknown density matrix. Let's check it for purity. And we see that the trace of rho squared is 1. So it's pure. This entangled state is pure. And it is as much as we can know about this composite system. We're living on now, the sphere that you would try to represent it on is not going to be so simple to visualize because we're in a higher dimension, harder to visualize. But the point is, even though we lose the visualization, the math captures what we're trying to say. And so this is pure. But there's a process of discarding certain parts of the system. Suppose you have the electron in your lab, but the positron's 10 light years away. They can still be entangled over that massive distance, but you might not know what the state of one of the systems is. And so there's a way of looking at the reduced state. So the total state is this pure state, but the reduced states, you might recognize them. There are these states that have trace 1/2. They live at the center. They are completely unknown. The state of the electron or the state of the positron, either or, both of them are completely maximally mixed. We have no idea what state they are in. If you only have one in your lab, this is all you can say about it. It's living at the center of the Bloch sphere is as bad as it gets. This is, like I said, what every company is trying to avoid. And yet, so we've started with a pure state, but if you only have one of them, you don't have access to the other, you can't say anything about the other particles. And so this is what I was trying to emphasize, and what I think as you go through more and more quantum will become more clear, is that it's like knowing everything about a car. It's like knowing that pure state up above, but trying to look inside and see anything about the individual particles leaves you in a maximally mixed state. It leaves you with no information. And so this is like sort of the hallmark of quantum entanglement. This is like one of the most weird properties that they have. And yet it very much is a property that companies are aware of and are trying to avoid. And what it means is if you're mixed at all, if you ever measure your state, and there are ways of quantifying how mixed you are. When I say quantifying, I mean measuring it in the lab. If you find that you're in a mixed state, that means you must be entangled with something else. And the worst possible case is that you're entangled with the environment and you're left with a mixed state because you're entangled with that environment, which you can't describe. And so the whole goal that these companies have is to fight against that entanglement with the outside world and keep all of the entanglement just in between the qubits that they're trying to control. And that is really the essence of entanglement that I wanted to, the point that I wanted to drive home. Even if it doesn't make sense right now, as you iterate through, you take quantum 1, you take quantum 2, maybe you end up going to grad school. I feel confident in saying that as you learn more and more about it, I think you'll come to appreciate this analogy. I think for me at least, it's been a nice way to frame my thinking about entanglement. And it actually is one of the key components of the idea that went into a recent project I worked on with people at Los Alamos National Lab in New Mexico. The full paper, if you'd like to access it, is at this link below. I think it's definitely, very technical, and it doesn't exactly explain things. Journal articles rarely ever explain things to people other than the exact practitioners of that very specific subfield. So, it's not exactly an easy read, but if you, need help sleeping, you could print out a copy and have a look at it. But the key idea that underlies it is exactly what we've talked about. If you have a bunch of qubits that, an n qubit state, and you want to see how entangled is it with and we're assuming that it's not entangled with the environment. We're assuming that we have a perfect isolated system, and we want to quantify the entanglement within that system. Well, we can look at, we can basically disregard n-1 and just look at one of the particles and say, okay, how mixed is that? Well, if it's maximally mixed, then we know it was really entangled with the other particles. Now we can, maybe look at just two of the particles and disregard the other ones and look at those reduced states and see how pure is that and check the purity. And basically what the quantum computer does for us is it computes all these different options, all these reduced purities, and takes an average effectively. And it gives us this number out that corresponds to the total entanglement within the state. So it's the exact idea that we were talking about on a few slides before about looking at the purities of reduced states. We've ignored, say, in this state, we've ignored 2. In this state, we've ignored 1, and we've just looked at the reduced purities. But with n qubits, it gets a lot more interesting. You have a bunch of different cases to consider. And so that's sort of the gist of this paper. I didn't want to get into the technical details because I thought it was more important that you come away maybe with some intuitive picture of entanglement in the EPR paradox and why it's so strange. And so I'll just close with a little bit about, when I was a freshman, I did not understand what the difference was between theoretical physics and experimental physics, other than one is in a lab and one's on a computer. I really didn't have any sort of nuanced view to it. Turns out it's pretty much that. But when there's a global pandemic going on, I will say being a theorist is a benefit, I guess, more so. It still sucks. You miss talking to people. You miss working through problems on a board with someone else. But like this collaboration I ended up having with Los Alamos was only really possible because of the pandemic. We were able to do all this work on Slack and on Zoom and whatnot. So, there was a bit of a perk. I don't think you should plan your career around the possibility of a long-standing pandemic. I'm just saying that, everyone had a tough time with Zoom classes and with this and that. Experimentalists, I think, were hit harder than theorists, just because it was really, at a certain point, you couldn't even go into the lab. So yeah, but my research, nowadays, I do everything on an iPad, take all my notes on an iPad, do all my calculations on an iPad. This is nice. You just send it to someone if you want them to check it. And I use a computer, the software called Mathematica, and programming language maybe you've heard of called Python. There's also like MATLAB, there's C, C++. Highly encourage everyone that's thinking about going into physics or engineering to become comfortable in one programming language. It depends which route you're going down, but you're going to need it regardless. And the cool thing is, if you completely burn out and decide, okay, physics isn't for me, well, you still have this really marketable skill, and you can go get some more training and do pretty easily roles like software engineering, data science, these things that they're very marketable, but they require this programming ability. And I know several PhD students that took some time off and did software jobs before coming to do their PhD and different things like this. So I guess if I, could sort of suggest two things, it would be learn to program and learn linear algebra really well. I think those two things are things I wish I had been told when I was younger. And the cool thing, I guess, about grad school, like a PhD in physics or computer science or math versus, say, going to med school, is we don't have to take out exorbitant loans to do so. We actually get paid. It's not a lot, but it's certainly enough to live on. And it's probably one of the few times, if not the only time, you'll literally get paid to learn. So, that's honestly a perk. And so, yeah, like I showed on the first slide, in normal times, pre-COVID, BC, as I like to call it, before COVID, we would be able to travel to conferences, and the university pays for that, and workshops to learn and share your research. And so, it is really cool. And if you have any other questions, please reach out. I really am excited and about CU Prime and about helping students get undergraduate research positions, and just about figuring out what it is that scientists do. Because that's the people that helped me when I was very eager, but sort of didn't know a lot. I always look back and I'm thankful for those people, and they're the reason that I was able to get to this point. So please feel free to reach out. I hope you gained something from the talk. Again, I wish it had been in person, but I appreciate you sticking with it this long. And yeah, I'll just conclude there. So thank you all for your time.
Great, thanks so much, Jacob. You can all give your virtual applause. And if we have any questions, then you can go ahead and just unmute, or you can put it in the chat. But we have a few minutes for questions.
Hi, Jacob. Can you hear me?
Yep.
I want to ask you about your experience in UK, more specifically. So the UK grad student, as far as I know, was for master was only 1 year, right? So my question is that year worth it? So, and what kind of what were you doing in the year that you get your master?
Yeah. Thank you for the question. And I can elaborate a little bit on it. Yeah, it was a program. It's called the Fulbright program, but there are other similar sort of. So Fulbright is an exchange between the U.S. and a bunch of other countries, and you can check their website. And so if you're interested in doing sort of a year abroad, studying physics or anything else that you're passionate about, that's a cool avenue to do that. And it's sort of an exchange in that some students from the UK came to the US, and then 50 US students went to the UK. So I would say that the primary perk of it, this is not like sort of the most pragmatic statement, or maybe this isn't what you would want to plan, I don't know. It's as good a reason to plan something as any, but the friends I made in the program definitely changed sort of how I view the world, and I'm still friends with a lot of them. And it was just a lot of people doing a lot of cool things that I wouldn't have met otherwise. So that was, in hindsight, that's one of the biggest perks. But when I was applying, I wanted to do it because I really enjoyed the research that I had done in this REU, this summer program. And I wanted to do more of it, but I knew that there weren't, I knew that like CU and the other places that I was applying didn't really do that type of research. So I wanted more experience doing this type of research, but I didn't want to commit to, the places in the US that did this kind of research were like MIT, which I pretty much assumed I wasn't going to get into, Caltech, same thing. And then like LSU, which is in Louisiana, and I did not want to live in Louisiana. So I just chose to apply for this year abroad to try and do more of this research. And yeah, not just because of the research, but living in a new country, I think, you saw on the first slide, I pretty much went to school. I guess I didn't give you a scale bar, but I pretty much went to school about an hour away from home. Tiny school, like 5,000 total people. I graduated with 3 other physics students in my year. There were only 3 faculty in physics. It was really a tiny school. And I did not feel at all prepared to come to Boulder, one of the largest physics programs in the country, and so I wanted this extra year of experience. And I think a gap year in any form can be really a really helpful step for people making the transition from, I guess since you're all at CU, it's really not the transition from a small school to a big school, but I think at a large school, it can sometimes be more competitive to get research experiences. And you might want to branch out and see about research experiences at a national lab or at a company, an internship in industry, these sorts of things. And I think for me, that year abroad was really about preparing for coming to CU. And yeah, I think I would highly recommend it to anyone interested applying. It's just cool to live in a different country for a year. And, I guess if some of your international students here at CU, then you understand that you learn a lot, about yourself and about others, leaving your home environment and entering a new one. So anyway, I hope that gives you some more context. Cool. Any other questions? And
so we have one question in the chat. Michael is asking if you could elaborate on what you meant by ket notation.
Yeah, let me go back here. Yeah, so these things here with a sort of vertical line and then this sort of right angle closing it, this is called a ket. When we take an inner product, and Dirac invented this notation, and like a lot of notations, when you first meet them, they just seem annoying. But as you go on, you see, okay, they were onto something. That's the reason it's still around. People don't keep ugly, inefficient notations for 100 years on accident. They're really useful. And the ket just represents the vector, the state vector. And there's something called a bra that it corresponds to, flipping the vector in a special way called transposing. So your column vector becomes a row. And the reason he called it that is because when you do an inner product, you write a bra, which would be this ket flipped along the vertical axis. And it would basically, I guess I should have tossed in an example of this, but it forms a bracket or a bracket. And so that was his sort of way of summarizing a nice notation for quantum states. And the reason is we have to take inner products all the time. A lot of quantum mechanics ends up, when you actually want to compute things that you might predict an experiment, something happening, you're going to do some inner product. And so you're going to take a bra and sandwich it in with a ket. And it reminds you the ordering of things so you do the multiplication correctly. It's really like it's a notational tool, and it turns out to be very good. Leonard Susskind, like I said, the book that I recommended all the way at the beginning, Theoretical Minimum. by Leonard Susskind. He has one on classical mechanics. He has one on quantum mechanics. Highly recommend both, but the quantum mechanics one goes over Brockett notation. Plenty of resources online. If you search Brockett notation, if you search qubits, you'll see these. And as you go further in your undergrad education, you'll see it time and time again. So hopefully that, I don't think I can meaningfully give you a good understanding of it until you start doing some computations with it. All I can say for now is Dirac invented it because it turns out to be a really clean way of expressing things. Cool. Any final questions? Thank you for the people that asked questions so far. All right. Well, if not, thank you all for bearing with a lot of new jargon and a lot of new notation. I hope if you're interested, you'll reach out. Please ask Tyler for my email. You can search it on the server, like the Gmail server, whatever. But some people misspell my last name. The last name's Beckey. So if you just email Jacob Beckey at colorado.edu. Happy to answer any questions you might have about undergraduate research or research going on at CU. Doesn't just have to be my research. Anyway, see the chat. Cool. Sweet. Tyler, everything?
Great. Yep. Thanks for coming, everyone. We'll go ahead and wrap things up here.
Awesome.
Yeah.
All right. Thank you all.